Hello and welcome everyone. So let's give this one a go. This time we're going to be looking here at the Empire State Building, something a little bit closer to home for many of you here. So we'd like to determine the height of the Empire State Building to the nearest foot. The information you're given is that there's a 28-degree angle here, and there's a 3,097 feet. That distance from the base over here to the top of the building like this. So while you're working on this here, ladies and gentlemen, getting this one down, trying it out, I want to mention here one thing that I forgot to mention in the previous video here. There's some terminology that we have. So if our person, let's say our person's over here, right? This angle here from the horizontal looking to their site, looking upward here, this angle here is known as an angle of elevation. Because it's basically how high up you have to look to see the top of the building here. On the other hand, if you have a person up here, if there's a person on top here, and they're looking down like this is known as an angle of depression. Okay? And you'll note here, so basically, instead of from the horizontal, so it's a matter of perspective here. You'll note that the angle of elevation, angle of depression should be the same here because you got alternate interior angles with your two parallel horizontal lines, but I digress. Anyway, back to this here. So note how in this situation here, okay, so here's the height of the building. We'll call it H, and we see that again, now we have the height of the building, and we have a hypotenuse here. So we should just choose the appropriate situation here. In this case, we can choose sine. Right, because we have the angle, we have something opposite the angle 28, and we have this height here. So let's go ahead and calculate this. We know that sine of 28 degrees is going to be h over 3,097, right? So that tells us here, we can multiply both sides by 3,097. We get h equals 3,097 times the sine of 28 degrees. And that we can put into the calculator. So you can go ahead and do that. And you find that this is approximately 1,453.95 feet here. As you can see, I have that in my calculator, like so. And that rounds to 1,454 feet. Okay? So we can see here that this is approximately 1,454 feet, which makes sense here. Okay. Alright, so now we've determined that this here is 1,454 feet. And that's great. Awesome. So let's consider the following here. So what I'd like you to consider now is just this. So that's, this is where we're standing here. So where we're standing, we're looking 28 degrees to reach the top of the building. Now let's say here, we're going to start walking toward the building. We're going to go in this direction toward the base of the building here, right? Now as we go, and while we're doing that, we're keeping one eye fixated on the top of the building and also just making sure that we're not running into traffic or other pedestrians or things like that here. We'll try to avoid all that. Now, as we walk closer and closer to the building, it would make sense that the angle of elevation is going to increase, right? Because as you get closer, you have to crane your neck higher and higher and higher to maintain eye contact with the very top of the building here. So we can actually keep going like this here. We can keep going, keep going, keep going, keep going. So, eventually we're going to get to a point here. Let's say that instead of 28 degrees, we can now have a new thing here. So let's say that this happens to be... let's say that we now have an angle of elevation of 45 degrees, right? Now, how far away from the building? Well, wait a minute. 45, this is still a right angle here, so we have a 45 on top like this. So that means this smaller triangle here is an isosceles right triangle. So that means now this here, we're 1,454 feet away from the building, whereas over here, we were a lot further away. We could actually calculate what that distance is down here, but we've made a distance. And then we can just keep going like this, right? We can actually just keep walking and walking and walking and continue walking closer to the building. And eventually, let's say we're going to get down here, where in this situation, we're only 500 feet from the building. So how do we calculate that? What's the angle now? Well, I'm not sure. But maybe we can draw the triangle here, because, there's a bit of a noisy diagram now. Now that we're closer to the building, we know that we're going to look something like this here, right? So this is going to be 1,454, and we don't know what this angle is, but we know that we're now 500 feet away from the building, right? Okay. Now, I'd like to determine what this angle is here. I don't really know much about it, but I do know something very important here, right? in this situation, now that we have this 1454 and we have this 500, even though we don't know exactly what the angle is, we know that it has specific properties here. So this angle I'm going to call theta here. So this angle, this is a symbol here. This is known as theta. This is sort of the, I think, equivalent of the letter H in the Greek alphabet here, and it's sort of the traditional variable that we use for angles. So we call this theta here. Now, we don't really know much about it, but we do know that the tangent of that angle, tangent of theta, is going to be equal to the opposite over the adjacent here. In this case, the tangent of theta is going to be 1,454 over 500. Okay? Now, notice that this makes things a lot different from what came before. If you looked at what we looked at for the past 2 or 3 days here, all the times we were given the angle and we had to determine, we were trying to figure out unknown side lengths. Now it's kind of backwards. Now we kind of figure out, okay, now we have the angle. What happened? What angle was it? So in essence, if you think about what's happening here, we used to have this sort of situation here where you had an angle theta, you popped it into this thing called tangent here, or sine or cosine, and then out popped your angle, your number, right? There's your ratio here, right? But now, what I want to do is I want to go backwards here. I kind of want to see what happens if I run this if I run the video in reverse here. If I did this, something should happen, and I'd like to get the angle theta back. Now, if this box was tangent, this box is tangent here. If this box were a different operation, that'd be easier to deal with, right? If if this box, instead of saying tangent, was x squared, right? If you pop in a number and a square comes out, and so for instance, something like, say, you put 4 in and 16 comes out, in order to get the 4 back, you would have to undo the square, right? So in this situation, we need to create this idea of something that undoes tangent here. We want to find the angle whose tangent is a specific number here. So, as they often say, necessity is the mother of invention here. So we have this thing called tangent here. We can now also create this other thing here that that's the anti-tangent. It kind of goes backwards here, and it undoes tangent. So I'm going to define here. So I'm going to come back to this picture in a bit, but I'm going to define here what is known as the arc functions. In this case, I define arc sine, but similar definitions will apply for cosine and tangent. So each of the trigonometric ratios has a dual, one that undoes it. It's the arc function. We call it the arc function here. So the arc sine of a number x is the measure of an angle whose sine is x. So in this situation, we can start off with the sine of an angle is equal to x here. That is logically equivalent to saying the arc sine is equal to, the arc sine of x is equal to a. Now, you'll note there's a -1 here. This -1 does not represent an exponent. This does not mean raise sine of x to the negative first power. That's a completely different thing here. This is just a symbol that we're using to represent that it goes with sine, and it kind of undoes sine here. So, and you'll have similar definitions for arc cosine and arc tangent here, right? So in this case, arc cosine, right? Cosine of a is equal to x. The definition tells us here that arc cosine of x should be equal to a. And the relevant one for our situation here, if tangent of a is equal to x, that means we want to use the arc tangent here. So arc tangent of x is equal to a. Okay? So it turns out that these are going to be very useful to us here. So it's this third one in this situation that we're going to be using. But again, we can apply this to any one of the trigonometric ratios here. So let's go back. Now that we have this here, we can now go back to this. So this, according to our definition here, is logically equivalent to saying that the arc tangent of 1454 over 500 is equal to theta. Now, this means that the measure of the angle theta is this. That means it's going to be arc tan 1454 over 500. Now, just like any other number, this is a number. But it's not a very good looking number. This number doesn't tell us a lot of things. We don't know what this is. And this is where the calculator comes in. So again, just like with trigonometric before, I do all the calculations by hand and then use calculator only at the very end. So I'm going to go ahead and do this here, right? You'll note that in most calculators that the arctangent function, the arc functions here are going to be above the actual functions themselves. I have a T89, but some of you probably have an 84, 85. It runs on the same principle here. You'll note that in this situation here, right, you can see that I have sine over here. We have the arc sine next to it here. On your calculator, there are dedicated buttons for sine, cosine, and tangent. I don't have a T94, but you can take a look at it on your calculator, and then there will be, it's in small text above the buttons, things like this here, arc sine, arc cosine, arc tangent. So we're going to be doing that here. So now we can go ahead and do arctangent of 1454 over 500. And that tells us here that theta is about 71.02 degrees. So that means this is about 71 degrees or so. So notice that when we're only 500 feet, so if we go back to our original problem, if we're only 500 feet away from the Empire State Building, now we have to increase our angle of elevation. We have to look up at an angle of 71 degrees to reach the top of the building here, okay? Now, we keep that in mind, and we can notice that this angle is going to increase as we get closer and closer here, and the value of this is going to increase as well. So keep this idea in mind. We're going to be looking at an example here in a short bit.